What we kind of got to last time was we were looking at the particle in a box. We said we can set up an eigenvalue problem with the Hamiltonian Schrödinger equation. We could solve it, and we got a couple important things. We got the energy associated with an n function. Got to get to the right thing. We can get the energy associated with some function, some counting number n. That's going to be pi squared h bar squared over 2ml squared times n squared. And we had wave functions associated with those that were 2 over L. This was our normalization constant that we calculated by looking at psi star or psi and insisting that it's equal to 1 when we do that integral. Sine and pi over L x, where we are looking at some box that goes off to infinity on the sides and goes from 0 to L. We then did one other thing when we said we could calculate the average position. We said the average position was just L over 2. It was the center of the box. There's a couple other things we can do. We can actually look at what happens when we plot, say, n equals 1 versus n equals 2. And we can look at those different wave functions. And we can look at those different probabilities. I'm going to do my best to draw these. My apologies for my lack of artistic skills. But if we are looking at the wave function itself, if we've got just a, if we're looking at n equals 1, we've just got a sine pi, it's going to have some shape. Ooh, that is not quite a sine function, is it? It's going to have some shape that's essentially going to be like a sine function lumped in the middle at our average position, L over 2. And if we look at the second one, we're essentially going to have the same thing, except for we're going to have essentially an oscillation. Ooh, okay, trying. It's going to be something like that. We're going to have like a full sine from 0 to 2 pi for the n equals 2 case. That's if we're just looking at the function. If we look at the function squared, this first one looks the same, right? If we square this function, we get the same thing, pretty much. When we square the second one, we're going to get some distribution. Ugh, a little too high. It's going to look like that. And again, we can see that this average value of L over 2 still makes sense for that second case. So this is, the blue is if I plotted the wave function. The orange is if I plotted the wave function squared. That's the psi star psi integral. Not just integral, sorry, just the psi star psi. And we can see in this second case, again, because of the way it's symmetric about L over 2, the average value is still going to be L over 2. Notice that it's not the position itself, it's the average position. And so we can ask an interesting follow-up question, and that's to say, what is the deviation What is the deviation of the position? What is this thing we would call, some people like to call it the variance. Essentially what we're going to be looking at is this sigma x squared. This is going to be the variance, similar to the idea of deviation. We're going to look at the position and how it is different than the average position. And we're going to take the square of that so we're always getting a positive value. So if x is lower than the average or x is greater than the average, we're going to square it so we always get a positive value. Now, through some mathematics that's not really that essential to us, we can rearrange this and we can get this instead of thinking about it in terms of position, because remember, our functions are not eigenfunctions of position. They're also not eigenfunctions. If I do the FOIL, it's not going to be eigenfunctions of position squared. So what we can look at is we can look at x squared minus x squared. And this is essentially going to give us this idea of the variance. How does the position vary on average? How much does it spread away from this middle value? So this gives us a new thing to calculate. We've already calculated the the average x, and we can easily square the average x. But we haven't calculated this idea of x squared. And what's interesting is, while we can simply take our average x, I'll still do it. While we can take our average x is equal to L over 2, and our average x squared is going to be equal to L squared over 4. That is not true for x squared average. For that one, we actually have to do a different integral. To get the average value of x squared, we have to do essentially the integral psi star x hat squared psi dx from 0 to L. We actually have to do a different integral. We have to calculate this other value that's going to give us this idea of how much the position is spread from that average. Now, theoretically, we don't need to do this. We can just kind of look here and say, oh, we can see how it's spread. We could calculate. We could do a bunch of calculations, right? We could take just little snippets instead of looking at the average over the whole thing. I could say, what's the probability of finding it in just little snippets across, and I could get this idea of position as I limit my bounds of my integral. But this is going to give us a kind of broader idea that we're going to be able to scale to other problems as well. It's also going to do something neat. 1 through 5, Heisenberg's uncertainty principle. Couple zeros, couple fours. So this is something that we introduce in general chemistry, and I really say introduce in a loose way because it's just kind of like, here it is. It's something that you see in pop science and like pop culture a lot, quite a bit, to say, oh, you can't know things. It's probably, in my opinion, is one of the most abused science things from quantum mechanics. That's just like people get it all wrong. It actually is something that we can completely derive by looking at this idea of how does the position vary, how does the momentum vary. And if you remember back to the first day, we said that position and momentum were inherently linked. That was part of, I don't have it written there, but it was part of like the Hamiltonian had the fact that position and momentum were inherently linked. We can also see it because position is x and momentum is derivative with respect to x. So we see that they're inherently linked. That's going to create some interesting consequences in terms of how much we know about each. So to get to that, let's go ahead and solve this thing. Looking at my notes, I'm going to do it generically for an sine n pi over L. So I'm going to do it generically for our generic wave function. I'm not going to pick a specific wave function. Follow along with me. So we want to solve for x squared. We're going to say that's going to be the integral. We can already kind of see what's going to come. The 2L is going to get squared because I've got that wave function twice. This is a completely real function, so the complex conjugate just gives the same function back again. I'm going to get a 2 over L integral from 0 to L. I'm going to have an x squared sine squared n pi over Lx dx. I did about 3 rearrangements there all at once. So make sure that you followed all 3 of those rearrangements. Thing number 1, I took the complex conjugate and said, oh, that's the same thing. Number 2, I plugged that function in both times. I moved the constant out. I collected my sine terms. I did all 3 of those things all in one sentence, one mathematical sentence. So please make sure you followed all of that. At this point, I'm going to need your help with your integral tables. Whoa, I am tripping over my tongue today. Your integral tables. The integral of x squared sine squared. Yeah. Oh, hold on, I can't hear. Someone's got it already. You're all too slow. 2 over L is going to be x cubed over 6 x squared over 4 Is that minus inside the sign or outside the sign? Okay, minus.
X cosine of 2x all
Divided by 4? 4. All evaluated from 0 to L. Now I have to do a couple things. I have to plug in the fact that I have an n pi in a couple places. So I'm going to end up with, if I'm doing this as an n pi, sorry, now I have to flip to my notes. I forgot that yours didn't do it for a coefficient up front as well inside the sign. I'm going to have an a there, If I'm doing n pi x, let me do a couple things real quick. If we're calling n pi over L some constant a, we're going to end up with a couple other things that are not on your equation sheet, unfortunately, your integral sheet. I'm going to get a there divided by a there. That's a 6. I'm going to get an a up front there, a squared, and an a there. So if I've got this coefficient out front, this n pi over L, I'm calling that coefficient a for this integral. There's a couple places where we have to plug in the fact that that a is going to come along. If you're like, well, how did you get that? Integration by parts. You have to do that whole thing. I'm not going to ask you to do it. That's why you have the integral table, is so you don't have to do integration by parts, except for a couple weird cases. But those are where the a's come out. We're going to find that that isn't going to have a huge effect. But let's go ahead and evaluate this in the couple spots where we need to evaluate it and trying to figure out how I want to move the boards. Let's do it like this. So I'm going to evaluate this up over here. So I'm going to take this whole thing. I'm going to evaluate it. That's going to have the 2L out front still. I'm going to have the x cubed. So that's going to be an L cubed over 6 minus 0. Don't care about the minus 0 because x to the 0 is 0. Minus, going to the next term, that is going to be, do I want to do all this? Yeah, let's go ahead and do all this. Well, I've got the answer, and I'm just like, how much time do I want to take plugging this in? Because I'm sure you can all do this. That's going to be an L squared over 4 minus 1/8. Oh, whoa, okay, this makes it easier. Since A is n pi over L, sine of 0 is 0. Sine of n pi, since the L's are going to cancel, 0. This whole term is actually going to, when we apply our boundaries, that whole middle term is just going to go to 0. Whew, thank goodness. I was like, wow, this is more complicated than I thought. So I can ignore that entire middle term. That whole thing goes to 0. Make sure I'm not wrong about that. Okay. Okay, yep. So we've got the L cubed over 6. When we come to this one, we're going to have cosine of 0, 1, and cosine of 2 pi, 1. So we're going to get something out of this last term that we have to pay attention to. So let's go ahead and pay attention to that. When we do the cosine, this gets easier still. Let's do the L term first. So the A is going to be an n pi over L times L. I didn't forget something, did I? That's what. Okay. What's that?
Don't A cancel out because there's an A like in the numerator?
Yeah, there is. I wonder why I have it written that way. One of these A's canceled. I'm going to leave it like that just for a moment because I'm not sure why I wrote it that way. Probably because I was copying it off of a different integral table. But I'm going to plug in my L there. Then I'm going to have cosine of 2 pi. The 2n pi. But 2n pi is always going to be some factor of 2 pi. The L's cancel out inside there. Divided by 4n pi over L squared. And then I'm going to ignore the last term, actually. I said, what's the cosine of 0? But notice, because it's got the x out front, it's going to be 0 times that whole thing anyway. So this is all we have to actually worry about. If I simplify this a little bit, I'm going to bring the 2L through. I'm going to cancel out. I do have this extra factor for no reason. Question?
Should it be a plus instead of a minus? Because like it's a minus, but then it's also a negative A.
So it's going to be like minus this whole thing?
Right, but in the beginning,
I think I'm okay with my minuses.
Yeah.
Okay. Always check my minus signs. That was the other thing I was going to say before I started this video. I missed a minus sign in my momentum operator in last class. Sorry about that. We'll catch that in just a moment. Remind me of that if I don't remember it. So I can rearrange this. I can bring my 2L through. I can cancel out. I don't know why I got that extra factor of A. We can cancel that out. And we can say that the cosine 2n pi, since it's always going to be some factor of 2 pi, that thing is just going to be equal to 1. And we end up getting L squared over 3 minus L squared over 2n squared pi squared. So that is this thing flipped over, a factor canceling. I think that's right. I hope I didn't mess that up at all. So what this gives us, again, the reason we did this was so we could figure out this idea of how the position is going to vary, right? So we now can look at this in a kind of obtuse way and say, okay, well, now we can say how the position is going to vary. If I've got this x squared value, this average of x squared, I can figure out the variance of the position. Yes?
I think the L and pi terms in the second term should all be to the power of 1.
Should all be to the power of 1. Let's see if I messed that up.
Because if one of the A's cancel out, they end up being to the first power.
If we cancel one of the A's, we're still going to have L squared, but you're right, the n and pi's are going to be the 1s, right? Because there's the x here. That's going to give us another factor of L. Oh, right, there we go. L in the denominator up front, when it comes through, is going to cancel that, so we are going to end up with L. No, that can't be right. Because this is going to be average position squared. Both of these have to be in terms of L squared. They have to be in terms of distance squared. Right? We can tell that just by looking at it. So,
So that's right, they are
it should be L squared still. Should it still be L squared?
Yes.
Okay. There's a quirk here. So let me write down. So the thing that I know is right. So I think where my problem is this A out front. I think that A out front is actually not supposed to be there. Because what I know, the part that I know, and I'll tell you I know this part for sure. This term, I got that part right. I think where I've messed up is I think this A is not supposed to be out front. I think that's what's throwing me off by a factor of n pi and out. I thought it was curious that I had it there in the first place. I don't think it's supposed to be there. I don't think it's supposed to be there. So, and it's 2 on bottom. Let me just make sure I've got that right. 2n pi squared. Yeah, so that's right. That I've got right. Like I said, I think that's what's throwing me off. I'm sorry about that. Yes?
Would that be an okay way of checking your work? Like a variance with...
Yeah, so again, everything in quantum mechanics still has to follow unit analysis, right? Just because we're doing this weird stuff doesn't mean we can ignore units. If I'm doing something that's in terms of position squared, I know that both of these, if I'm doing this in meters, just because meters is easier to think about than nanometers, if I'm doing this in my positions meter squared, the lengths are both have to end up in being squared, so I get meter squared. Same thing with my average position. It better be in units of just distance, not distance squared or distance cubed. It better just be in distance. We're going to see the same thing when we look at our momentum. It better be in units of meters. Ooh, momentum is kilograms meters per second. Same, yeah. So it better be like the same type of idea, right? Our units still need to be consistent. So, sorry about my math flub there. Like I said, I think it's just that extra A term. I think that's it. So I'm going to go ahead and erase that mistake and just plug in this value of x squared here. So we can look at what this gives us in terms of the variance, the way that it deviates, the way that the position deviates. So I'm going to have L squared over 3 minus L squared over 2 n squared pi squared. This gives us a kind of curious result in terms of position. This is going to give me, if I plug these two things back into my sigma x squared, I'm going to get my variance is equal to this term, L squared over 3 minus L squared over 2n pi, minus this part here, L squared over 4. And notice everything's in terms of L squared. That is because I've got my average position squared. So I should get something that's all in terms of position squared. This essentially, and then I can collapse a couple terms. I can simplify this a little bit. Yeah.
I think if you have the square in the denominator for the 2 and 5.
Oh, I sure did. Yes. That is still squared. That's supposed to be squared. So if I go ahead and rearrange this a little bit, I can take out now a common L squared factor. I'm going to do something. Do I want to do that? I'm going to do something a little bit strange. No, I'm going to leave it like this. I like it like this. We can take out that L squared factor. And then we're going to have essentially, I can do 1/3 minus 1/4, or I can do that as 3/12 or 4/12 minus 3/12. And I'm going to get 1/12 minus 1 over 2n squared pi squared. So what this tells me, what this tells all of us, is that there is some variance that's going to depend on an inverse n. Right? There's some variance that's going to depend on n. And as n goes to infinity, I essentially have an upper limit for how much for that variance. This tells us two things. First off, if the size of the box gets really, really, really tiny, I'm more certain of where the particle is. That makes sense. If the box gets small, if this term goes to 0, I'm really certain of where the particle is. Conversely, if the box gets really, really, really large, I become less certain of where the particle is, because that L term is going to make it get really large. So in this sense, I can say that there's some direct knowledge between the variance of the particle. Its average position is going to be in the middle of the box, regardless of how big the box is. But the variance is going to get larger and smaller as the box gets larger and smaller. Questions about that? So the next part we have to do is momentum. So we're going to calculate a couple things. We didn't do momentum last time, did we? Oh. So a little bit more to do than I thought. Let's erase that. So I want to find average momentum of the particle. You should all be able to set up this problem before I set it up at this point. You should be able to write down the integral that I'm about to write down before I write it down. And we're going to do just the x position. We're still just doing 2D boxes. Px hat, psi x, dx. I have to plug in what psi is and what p is, what the momentum operator is. And this is where I made a mistake last time. It didn't come up very often because as long as you're squaring the momentum operator, the negative sign disappears. But the momentum operator is negative I h bar d by dx. I forgot my negative sign. Most common mistake in quantum mechanics, forgetting a negative sign. Yeah?
In this class, will we be evaluating momentum only in one dimension?
We could do it in multiple dimensions. We're gonna see how, at least for the particle in a box, when we expand momentum, it actually doesn't get any harder. It's a momentum and position. It doesn't get any harder. It's just kind of like doing the same problem twice. But for now, we're just going to look at it in one dimension. I forgot that negative sign. Since everything we did last time had momentum squared, I didn't notice. But as soon as I went to do this problem with just momentum, I was like, I'm off by a negative sign. It was driving me crazy. Don't forget your negative signs. So we can go ahead. We can plug in the wave functions. We can plug in the fact that the wave function is going to be real, so we get the same thing twice. Ooh, not quite. We have to apply an operator. So when I do this, I can't be as cavalier as before. I still get the 2L out front. I'm still going to have this integral from 0 to L. I'm going to have a sine n pi over Lx. I'm going to have my momentum operator, negative I h bar d by dx. And that's going to be operating on my sine n pi over Lx dx. Kind of goes at an upward slope. This operator is going to change that sine to a cosine, of course. The IH bar is going to be a constant. I can bring that outside. The sine is going to flip to a cosine. And I'm going to have the integral of sine n pi x cosine n pi x. I'm also going to have an n pi L end up on the outside. Let's see. I'm going to write this off to the side because we're going to want sigma x in just a little bit. Sigma x squared is L squared over 1 12 minus 1 over 2n squared pi squared. Okay. Okay, so the integral that we have to solve, I'm going to move the IH bar out, so I'm going to have negative 2I H bar over L. integral from 0 to L sine n pi over xl cosine n pi x. Ooh, huh. Sine n pi x divided by L cosine n pi x divided by L dx. Oh, and the n pi over L, right? Because when we take this derivative here, we're going to get n pi over L cosine n pi over L x. Let's move that n pi over L. Those are all constants, so let's move that out here as well. So I'm also going to have, ooh, let's just move this over. Negative 2i h bar over L times n pi over L. That factor from taking the derivative needs to come along as well. Integral tables again. If I remember correctly, this integral is a little bit easier. Someone help me out. That? Oh, negative cosine squared ax. Okay. So let's go ahead. Let's bring out the code. Let's plug in what our a is. That's going to be n pi over L. Let's plug in our a. That's going to be n pi over L. Negatives will cancel out, and this is going to be evaluated from 0 to L. All of that keeping track of constants didn't matter. Because when I plug in, this is something we saw last time when we were doing, I can't remember which part it was, but we were doing some integral and we had two parts and we had a cosine part from 0 to L that was like this. And we noticed that when we had cosine of L, cosine of n pi, cosine of n pi is 1, cosine of 0 is 1. This term goes to 0, which means this whole integral goes to 0, which means our average momentum is 0. There are two possibilities for what it means if the momentum is 0. What's possibility number 1? Yeah?
It's traveling the same.
That's the interesting one. What's the boring one? Boring answer is nothing's moving. Now the interesting answer, right? So if average momentum is 0, it could be that it's just sitting still doing nothing, which is not actually interesting. It's not actually what's happening. The more interesting answer, the more interesting possibility is that it's equally moving in the forward direction and the backward direction. If we take the average of the particles essentially, we can make classical sense of this. Remember, I want to warn you again to be careful with your classical analogies. We can make classical analogies, but they always break apart at some point. So if we imagine that our particle is something that's bouncing back and forth inside this box, it's just bouncing back and forth inside the box, and its average momentum is just back and forth. That's going to be an average of 0. That's also, if it's bouncing back and forth, if it's not slowing down at the walls, that's also why the average is the middle, because often it's in the middle, right? So we can kind of think about it in those classical ways, but classical things only work so far in quantum mechanics. There's another way that we can make sense of the particle essentially being momentum in two directions. That is to say, when we look at this, I shouldn't have erased that. If we look at the momentum operator, actually we can just see it up here. When we applied the momentum operator, we didn't get the same function back. We switched from sine to cosine. That means this function while it is an eigenfunction of the Hamiltonian, the eigenfunction of energy, it is not an eigenfunction of momentum. So it allows us to figure out the eigenvalues for energy, but it doesn't allow us to say too much about momentum besides the average momentum is 0. And then we can also look at the variance, that spread of the momentum. Another thing we could do, if we wanted to say something more interesting about momentum, is we could rewrite psi of n using that Euler decomposition we talked about last time. We can rewrite this using the Euler decomposition. So remember, what we could say is e to the I kx is equal to cosine kx plus I sine kx. And e to the minus I kx is going to be cosine kx minus I sine kx. If I subtract these two functions from each other, the cosines disappear, and I get a 2I sine. Yeah?
Before you do the Euler decomposition, how did you get all those in terms of E?
This one here?
Yeah.
That's what I'm showing with this.
Okay.
Right, so I just wrote this down without explaining where it came from. This is the explanation for where it came from. I've got these two ways I can write the functions. And if I take these two functions and I subtract them from each other, I just get sine. Oh, I get a 2I sine. Divided by the 2I, I just get sine. So those two things are actually the same. Now, there's benefits and detriments to how we write these down, what we're trying to represent, what we're trying to show. But one of the things that we can notice is now this is two functions that are eigenfunctions of momentum. And essentially what I can say is I've got some momentum in the forward direction and some momentum in the reverse direction. If you remember back to the completely free particle, we had a positive momentum and a negative momentum possible. We see the same thing happen with the particle in a box, which is not surprising because this is essentially just a restricted free particle. The reason we did everything in terms of sines and cosines is the boundary conditions to get the quantized energy and the coefficient up front. The boundary conditions are a much bigger mess when you're doing the e's, the exponentials. We could have done it. You should do it as homework for fun, but it is a little bit more mathematically intensive. So, momentum 0. Or, sorry, momentum's not 0. Average momentum is 0. Momentum's not 0. Average momentum is 0. So one of the things we can definitely ask then is, well, what about the deviation? What about this variance of the momentum? Are you ready for that? Okay. If we want to get the variance of the momentum, we're going to use a similar equation. We're going to have that sigma px squared is going to be equal to p squared minus px squared. We already know that back term is going to be 0 because the average momentum is 0. What's going to be more interesting is this front term. And it's not going to be that hard to calculate because p squared is kind of like the Hamiltonian. We've kind of already done this. So I'm going to write down I got my 2 over L still. I'm going to have my sine n type L over x. I'm going to have a negative I h bar d by dx squared on sine n pi over Lx dx. Right? Same kind of setup, same kind of thing we did before. Except for now I'm going to square this thing. I'm going to bring the h bar squared out. The I squared is going to be a negative sign. I'm going to bring that out. Oh, yeah, that's going to be a negative. Oh, no, it's not. Wait, no, it is. Okay. That's what I messed up in my notes when I was doing this, and I was like, wait a minute. This is going to be a negative I squared. The negative is going to square. The I is going to square. That's going to give us a negative. We're going to bring that out, and we're going to have d by dx squared on psi n pi over L. We all know where that's going to go. Notice this is essentially just the Hamiltonian off by a factor of 2m, right? There's the 2m we have for the Hamiltonian is not there. Everything else is the same. H bar squared, apply the derivative not once, but twice. That's going to give us n squared pi squared over L squared sine n pi over L x. Did I forget a negative sign?
Yeah.
Oh, I forgot a negative sign. This is going to have a negative sign outside of it as well. Oh, thank goodness. I wanted that negative sign to disappear, and now it is. So thank goodness I remembered both negative signs so we could ignore them. So I'm going to bring out all of my constants. I'm going to have a 2 over L h bar squared n squared pi squared over L squared times the integral sine squared n pi over Lx from 0 to L. Give myself a little bit more space. Oh, did I erase too fast?
Yeah.
There. I wrote it just a little bit smaller so it didn't run into my other integral. And don't forget dx. Oh, that's convenient. What's convenient? Let me. I'm gonna write something down that I hope makes this a little bit more convenient to do. This is essentially if I get rid of that 2L. I'm gonna write just a little thing to see if this helps clear things up. H bar squared n squared pi squared over L squared. Integral from 0 to L psi star psi. For the same n value. Not 0. Yeah, remember, since this is the reason that I was like, oh, that's nice. We already solved this integral last time, and we know that it gives us an L over 2. If you don't remember that, we can go through it again. Here's the trick that makes life a little bit nicer in quantum mechanics. If we pay attention to what functions we're using, particularly the fact that we're using an orthonormal basis set, right? If I leave my square root of 2L here, my square root of 2L here, take the derivative twice, that's going to give me this term plus the function back. Essentially, I've got my momentum squared term times psi n star psi. Because it's an orthonormal set, we know that integral is going to go to 1. Right? That was the integral we did last time to normalize this thing, to guarantee that that integral was equal to 1. If you don't remember that, you should be doing your homework. Those problems in the textbook, I'm not assigning. It takes me a while to get, because the version, the 10th ed and the 11th ed are pretty different. It takes me a bit to get through and find all the problems that are pretty much the same. So I'm not doing that for my own benefit. I'm hoping you're actually doing those problems. So, if that integral is equal to 0, I'm sorry, not 0, 1, the normalized version, not the orthogonal, then that's going to give us our px squared is equal to h bar squared is equal to this thing out front. H bar squared n squared pi squared over L squared. Now this is interesting in the way that is contrary. You can't see it well enough there. This is interesting in the way that it's contrary to what we found for the variance of position. If I go ahead and I actually plug this in, since the first term is 0, my variance with respect to px is just going to be h bar squared n squared pi squared over L squared. So what's interesting here is if we remember when we were looking at our variance with respect to position, we had it dependent on L squared. When we look at our variance with respect to momentum, it's the inverse of L squared. Question?
Yeah, so I'm a little confused about the 2 over L.
So that I buried back inside here. So if you do this integral, from 0 to L, you're going to get L over 2. And that was from, this is like the average integral. And so the 2L, L over 2 cancels. And that's I buried it back into the wave function so I could define the wave functions the way that I wanted to see the orthonormality. Back to after we get that, we say, okay, I've got the variance. This is an inverse. So while the position got more specific the smaller the box got, the momentum gets less specific the smaller the box gets. There's this, as the box gets larger, as we see our position get more uncertain, we see our momentum get more certain. We get a smaller variance in our momentum. We see this inverse relationship between the two, which might suggest I want to put the two together. Right? If I put the two together, I'm essentially going to cancel out that L squared term, and I'm going to see something interesting. Are you ready for that? Other questions before I do that? I just did quite a bit. I want to make sure I'm not rushing ahead too far just because I'm trying to fit everything in. Okay? Okay. So, what I'm going to do to illustrate something interesting is I'm going to take the variance with respect to momentum, the variance squared with respect to momentum, and the variance squared with respect to position, multiply them together, and what I'm going to get is some function that no longer depends on the size of the box. What I'm going to get n squared pi squared h bar squared over L squared times L squared quantity 1/12 minus 1 over n squared pi squared n. I'm going to rearrange this in a very intentional, very suggestive way. I'm going to bring my n squared pi squared in. I'm going to cancel out my L squareds, and I'm going to bring, oh, did I forget my factor of 2? I forgot a factor of 2 there. Don't forget your factor of 2. Yep. And I'm going to bring out a factor of 4. And I'm doing a factor of 4 because of the way it works out for where I know this should go. You would not do that unless you knew where you wanted it to go, and I just happen to know where I want it to go, so I'm pulling out a factor of 4. That's going to give me h bar squared over 4 times the quantity of n squared pi squared over 3 minus 2. Right, so if I pull out a factor of 4, this is like 2 times 1/4 is 1/2. Pull out the factor of 4. 2 times 1/4 is 1/2. Yep, great. 1/12 times 1/4 is a third. Great, that works. And the reason that this is important is because we know that this thing, for every value of n, oh, I gotta remember, greater than, oh. For any value of n, this thing is going to be greater than 1. If you do pi squared over 3, you're going to get something, for n equals 1, you're going to get something that's greater than 2. And then as the n goes bigger, this term's just going to get larger and larger. This thing is always going to be bigger than 1. That is to say, if I took my minimum, I could rewrite this to say sigma px squared times sigma x squared is greater than or equal to h bar squared over 4. That, which I just boxed, since I know that this is greater, since that term is always greater than 1, I know that this sigma squared x squared always has to be greater than or equal to h bar squared over 4. This is Heisenberg's uncertainty principle for position and momentum. This essentially says when I have constrained systems, when I have systems that are limited by some space like this, I've got some limit to how much I can know specifically about each thing. This is really impressive when we do it in a lot of other places. When we're looking at it in terms of measurements, when we're looking at it in Gen Chem, it's all really impressive. In my opinion, it's important, it's fascinating, but once you already have this limitation on what you can know in terms of position and momentum, it's less shocking next to everything else we've already done in quantum mechanics. But it's still a really important result that kind of brings together the idea of what we can and can't know in a measurable system. Now, one of the things, yeah, question?
Are we going to be doing this for other observables?
Yes. Right, so this worked, and that's exactly what I was about to go on to, is how we could do this generically. Right, because one of the reasons that this works particularly for position and momentum is because we knew they already had this connectivity between them. Right, the way that momentum is defined has something to do with position. Position is defined with respect to momentum in some regard. I knew that those two things had to be fundamentally connected to each other. So what's a more generic way that we can tell that these two things are connected to each other and whether any two other observables are connected with each other? This is where we bring the Heisenberg's uncertainty principle more in line with quantum mechanics. And we look at one particular question that goes beyond just the particle in a box and looks at all kinds of situations. That is to say, I want to know if the order of operation for these two values matters. So I'm going to say px, x on some function, and what I want to know is that equal to x, px on some function? Most of you will probably look at that and say, well, things commute, right? Like most things we do when we're looking at momentum, when we're looking at things in normal mathematics, things in our classical world, that idea of things commuting is always true. Another way to write this is to say, if I subtract this over, I could say, what is this equal to? If I'm looking at x hat px on some function of x, and I'm subtracting px hat x on some function of x, is that equal to 0 or not 0? Is that equal to 0 or not 0? What is that actually equal to? Most of what we've done in our lives with mathematics up to now would say, oh, these two things are 0, but we're doing operators, and as soon as I plug in the definitions of these operators, I think you'll quickly see that it's not 0. So when I plug this in, this is going to be x. Don't forget your negative IH bar. I'll just bring that out front. IH bar d by dx of psi minus negative IH bar d by dx of x psi. I have to apply the chain rule here. I can't just bring the dx over to the psi and say, hey, they're the same. I have to apply the chain rule. So I'm going to go ahead and apply the chain rule here. I'm going to move the IH bar completely out. Let's just take that and say IH bar times the whole thing, just so I don't mess up my negative signs. When I apply the chain rule's derivative of the first times the second, so I'm going to get negative psi of x plus the derivative of the second times the first, so that's going to be an x d by dx of psi of x. Negative IH bar up front. If I bring this term down, you'll notice this term is going to cancel with this term. And all I'm going to get left over is this is not 0. First and foremost, that's the important thing here. This is not 0. What I'm going to get is IH bar. The negative signs will get rid of each other, and I'll get IH bar is equal to x hat. Oh, first off, I'm already tired of writing that. We have a shorthand for writing the commutation of two operators, the x hat px. The way we write that would be x hat comma px hat in these square brackets. That means apply. That means this whole thing, right? That is how we write down the commutation. So I'm going to go ahead and write down the commutation of x hat on p of x hat. Sorry, I forgot my psi. If I apply this, I get a non-zero value. I get a non-zero value. That's weird. Generically, we can then write that this is going to be related to the variance. Right? If I take this and square it, so this would be related to the variance. And if I wanted to write a generic equation for this, you want to see the generic equation? It's a little bit ugly, but I'm going to write it right here for you. If I wanted to turn this into a generic equation for the variance, I would say for a generic pair of operators, for some operator A and some operator B, I would define the variant, the square variance of the two as equal to, greater than or equal to, negative 1/4 integral psi star, the commutation of A and B on psi. I'm going to do it for generic coordinate system d tau squared. So if we look back at our px, our sigma px squared, our sigma x squared, we actually see that this works out as expected. Now, to be fair, when Heisenberg first derived this, when he was first thinking about this, he did it in these terms. He did it in terms of two generic operators. I forgot my hats there. Two generic operators operating on some function and the limitation associated with those two operators. Fortunately, this is good news for us. This means there are things we can know at the same time. Any operator where if I take this, if I take the commutator of two operators and I get 0, that means I can know them both perfectly. For example, if we looked at, instead of looking at position and momentum, if we looked at momentum and energy, we would find that we can know both of those at the same time, right? Because d by dx squared and dx, those things can switch positions with each other. Those two things commute. So there are things that we're going to be able to know at the same time, that we're going to be able to perfectly measure at the same time, and there's going to be situations where we've got some uncertainty. So a lot of the time throughout the course, what we will do is we will look for those things that we can know without introducing this minimum uncertainty, this minimum variance. We're going to pick operators that commute with each other so we can know both of those things as measurables. We'll see that not so much when we do vibrations, but when we move on to rotations, we have to make some choices in the things that we can and cannot know. And it's going to be based on whether the operators commute or not. So that's going to become an important theme later on. Yes?
Can you go over the bracket notation that you...
Yeah, so let me go over the bracket notation. I'll do it for this AB here. So for a generic thing, if I wanted to look at A, B in a bracket like this, this is saying the commutator of operator A with operator B. That would be equal to A hat, B hat, minus B hat, A hat. Now, important thing about operators. Unless we have a function, this mathematical sentence doesn't really mean much, right? Operators operating on nothing doesn't make sense. So whenever we check for whether operators commute or not, we're always going to need some test function, some like psi of x or some psi that's in the coordinates of the operators. So perhaps a better way to write this might be, if we wanted to look at this on a test function, we would put a psi out front, and then that would be A hat, B hat on psi minus B hat, A hat on psi. Keeping in mind, we have to do the operations in order. So I have to operate B on psi and then A on psi for this first term, and I have to operate A on psi then B on psi for this second term. I have to keep track of that order of operations matters. And we saw that really clearly in our momentum position one. The order in which we wrote all of this down, and actually even the chain rule, making sure that we're doing derivative of the first times the second, and then doing first times the derivative of the second, that ordering is actually really critical now. We have to pay attention to it. In normal mathematics, chain rule, we can kind of like be a little loose with it. Here, we have to be really careful about the order in which we're doing things. Question?
If we'd written B comma A in the brackets, it would have been flipped down.
Yeah, so if we write B comma A, essentially we just get, oh, that's actually a great thing. Let's take a look at that. If we write B comma A, if I write B comma A, that's equal to negative A comma B. I don't know if you can see that. I kind of scrunched it accidentally. But yeah, you're going to flip your sign, and that's going to flip the order in which you do things. You're going to get a negative sign out. So flipping the order inside of your commutator gives you a negative sign up front. Question and then question.
So if that term equals 0, then we know precisely the both
Yeah, if that term equals 0, then our covariance, the variance of A and the variance of B together, is greater than or equal to 0. Right? We can know both of them at the same time without a problem. Other question? Same question. Okay. So yeah, that's going to be a really nice feature we're going to look for. Is that sigma A squared, sigma B squared greater than or equal to 0? Yes. That is kind of by definition. That is part of the definition that I threw in there. if we went through and did the full derivation, I have a textbook that actually goes through the full derivation and shows how you can get the 1/4. It takes 3 pages. I was like, I think I'm okay without.
Wait, so for any two things that can all be known at the same time, there'll be a negative 1/4 input?
When we're looking at this for the greater than or equal to for the minimum, yes, there will be that 1/4 term out front.
But if we know both of them, then it'll be 0?
It'll be 0, right? If we can know both of these, if the commutator is 0 and we can know both of the observables associated with our operators, then we'll have a 0 term. So, oh yes, good. I'm glad you're asking questions because I really didn't have enough time to do the 2-dimensional box, and I'm like, I don't want to squeeze it in, but I might try anyway. Yeah.
So by definition, it's negative 1/4. Why was it not negative? Like h bar down, h bar squared over 4. Why was that not negative?
That was because we got if we go through our mathematics again, we had a negative sign come out. If we actually do this, we end up with a negative sign, and that's where that comes from. Yeah.
Sorry, can you explain like the 0 instead of the negative 1/4?
So essentially, what we're saying, the reason we're looking at this, and let's look at it in terms of position and momentum again for a second before we go generic. What we're saying here is we went through the math today for how much we could say about the position of a particle in a box and how much we could say about the momentum of a particle in a box. The position, we had some average value, and then we could also calculate the variance associated with the average value, how much it moves away from that average value. We could do the same thing in that average was like the middle. We could do the same thing for momentum. We could say there's an average momentum, which is 0, and then there's a variance because the momentum's not actually 0, so there's some spread of possible momentums around an average of 0. And when we take those two together, it turns out that because of the way that these two operators relate to each other, the way that these two observables relate to each other through their operators, there's a minimum to how much we can know both of them, how much we can measure both of them at the same time. And we said, okay, that's great for position and momentum. What if we extend that to other ideas? And that's where we brought in this idea of the operator. When we bring in this idea of the operator, generic operators, we say if we calculated this thing and we had our operators, if we look at the order in which we're operating on things, if the operators can be switched in terms of which order we're doing our measurements, essentially, and how we're working on them, then this term would be 0. This thing inside of the integral would be 0. And our term here in terms of how well we can know the observables associated with A and the observables associated with B, that uncertainty, that variance would be 0. And we'd be able to measure both of those things without messing up how much we know about the other. However, in the case where this commutator, looking at the order of the operators does matter, we get this minimum uncertainty, this limit to how well we can know both of those observables associated with those operators at the same time. Does that help?
Yeah.
Great. Question?
Do you have any like exact operators that usually have like an exact goal?
Yeah. I mean, like, so, for example, the energy operator, right? We got a set of values associated with the energy operator. Now, the reason we got that was because we picked functions that were eigenfunctions of that operator. So it really has to get to choices we're making. And that's one of the things that I think makes quantum mechanics most daunting, is we actually get to make choices in terms of what we want to do and what we want to see. If you remember earlier, we set it up where we were like, oh, we can know the energy if we use the sign function, but not the momentum. We could get the energy eigenvalues, but we couldn't get the momentum eigenvalues. If we change the way we write down that function, we could get the energy eigenvalues and the momentum eigenvalues. We could know both energy and momentum. But we couldn't know position. None of the functions we picked were eigenfunctions of position. So that one didn't work. If we pick functions that are eigenfunctions of position, it messes up the other two things. So we have to make choices. And this whole time, for the last 3 classes, this is the 4th class, right? So for the last 3 classes, not so much the first day, but for the last 3 classes, we've been making choices about what we want to observe. And we've almost always been starting with energy, right? That's why we've always been starting with the Hamiltonian and been worried about the conservation of energy. That's been our starting point most of the time. Not so much position or momentum or those other things, but energy. Yeah?
So I think what you're saying is I agree with what you're saying, you can never know everything that you're trying to solve. So you have to like pick and choose.
Yeah. Right, and this also kind of gets to a funny thing about the wave function, right? The first postulate of quantum mechanics is the wave function tells us everything. That's assuming we can get the right wave function, right? And we're really dealing with parts of wave functions. We're picking parts that we can understand, and we're only dealing with parts that we can understand. We're not actually getting a full wave function that describes everything in the system all at once. Now, later on, we're going to see that there's some other ways we can represent all of this in terms of matrices. And there's a lot more information that we're getting than we think. And we can essentially, by choosing how we diagonalize the matrix and what we're using to label our rows and columns, we can actually switch what information we're talking about quite easily. But that's for the future. But there's like, while this might seem daunting of like, oh, can we really know anything? It's like, yes, but getting to that information is a little bit more complicated. And we'll get there. Which, for the last few minutes, I want to point out that the reason we've started doing this, I still have a couple more things from 7D that I want to do, but the reason we were doing the particle in a box, looking at momentum, looking at position, looking at energy, is because this is the first of our 3 major modes of motion. This is our translational motion. If we want to build up to understand atoms and molecules, even the simplest atoms and molecules, we're going to have to understand essentially 3 different types of motion. We're going to have to understand this translational motion, kinetic energy. We're going to have to understand vibrational motion. That's going to be really handy for describing like 2 atoms with a bond. That bond behaves very much like a spring, so that's going to give us our vibrational motion. And then that atom can also spin in 3-dimensional space. So we're also going to have to worry about our rotational motion. And of course, the molecule can move through space. That's what we've done already, right? That's the translational motion. So we've really done one of the 3, and then pretty much everything we do is just mixes of those 3 things. Sometimes we have things that are rotating and vibrating at the same time. Actually, we almost always do. But we're going to try to break those into separate, discrete parts that then we can build into more complicated things. So we've just handled our first type of motion, translational motion. Questions? Yes?
Does the vibrating and the rotating explain IR and NMR?
Explains IR,
Okay.
but not NMR.
Okay.
NMR, well, kind of gets, the rotational kind of gets to NMR, but NMR is really dealing with spin, which is not your traditional kind of like rotation. And I'll try to always be careful and use the term rotation for a physical object that's rotating, and spin, which is really not a good word for describing this quantum phenomena that's simultaneously magnetic moment and angular momentum.
But NMR is still quantum.
NMR is definitely quantum. NMR and the quantum mechanics of NMR is actually what I did my graduate work in. It's like there's entire separate book. Like after you get through like this textbook, there's like 4 other textbooks for NMR that's specific to NMR. If anyone's really interested in NMR spectroscopy and how you can apply quantum mechanics to NMR, after we get through rotational, talk to me. I can give you some PDFs that are really interesting. After we get through rotation, though, because it's going to depend heavily on that aspect. Other questions? So in terms of what we still have to do in Chapter 7D, we still have to talk about moving our systems to multi-dimensions, going to 2 dimensions and 3 dimensions. We're going to have a brief aside on tunneling, and then we'll be done with 7D. So we're moving quickly into rotation. Well, oh, and for those of you that are in 10th ed, 7D is 8A. So just pay attention to the material in the text, and we're moving quickly towards vibration. Just a reminder, quiz 1 will be next Thursday, midterm 1 will be in 2 weeks on Thursday. Come to office hours.